All right, gang, here we go. So this is Physics, Unit 3, Part 2. This is all about potential energy. All right, so this guy's going to be short and sweet. So remember, in the last video, we talked about work, and then we tied work into kinetic energy. All right, now we're going to talk about the other half of the energy thing, which is potential energy. So kinetic energy, remember, energy of movement. Now, potential energy is instead of the object moving, it's more of like a measure of how much energy could the object have if you suddenly just let it go. All right, that's kind of how I think about it. So like both of these examples here are, oops, my pen was not active. So both of these objects here are things that have potential energy. So if you pick up a book and just hold it above the floor, he's got potential energy, because if you let go of the book's going to fall and gain kinetic energy because it had potential energy, or had the potential to move, right? So then you let it go, it starts falling. All right, an arrow, so if you imagine you have a bow and arrow, right? You've got the arrow, you pull it back, okay? If you let go of that arrow, or the bow, right? Then they're going to start moving on their own. You don't have to move them. So by pulling that arrow back, attaching it to the bow with a string, it's got a potential energy stored up inside of it. All right. There are several types of potential energy. There's gravitational, elastic, and then electromagnetic. Okay. Gravitational, we're going to talk about a lot, right? Elastic, we're going to talk about a lot. This is also known as like spring force. Okay. Springs, and then electromagnetic we'll talk about next semester. All right. So gravitational potential energy. All right, this is the formula. Okay, so potential energy, PE, and then the G, you guessed that stands for, that's the gravitational part of it. Okay, so anyway, so potential energy due to gravity is equal to the mass times the gravity acceleration times the height. Okay, so the gravitational potential energy is created whenever you lift something up off the ground. Okay, so the SI units, these are the SI units. Primarily, we'll just use joules, but it's interesting to note that you should recognize this from the last one. That's the same units we had for work, right? And it's all in joules. Okay, and then the height depends on the zero level chosen, where potential energy of gravity is to zero. So essentially, we're just going to say, well, when we're on the floor, that it has zero potential energy because it can't fall anymore. Okay, and suddenly there's a sinkhole or something like that open up underneath it. All right, so that's a gravitational potential energy. Elastic potential energy is the energy that's available for use when you deform an object that will take its shape back, right? So if you take a rubber band and stretch it, it's got elastic potential energy, because if you let go of the rubber band, it's going to move on its own, go back, and you have to keep putting in energy in order to keep it apart, right? Same idea with springs. Okay, like think about a trampoline. We've all jumped on a trampoline. You go up on the trampoline, you jump down, and the springs on the side stretch out as you go down, but then once you've run out of kinetic energy going that way, the kinetic energy has been transferred to the springs, and the springs come back and compress again, pull up the fabric of the tarp and shoot you up in the air, or the trampoline shoot you up in the air. Okay, so those are potential energy. Okay, the important part about potential energy, or elastic potential energy, is this delta X value. So that tells us how much our spring was compressed or stretched. All right, so that's literally the change. So this is the full length of the spring here, right? From here to here. And then something came down and pushed it this way, right? And so now it's compressed all the way over here, and this is how far it got compressed. And so this is the compressed length of the new spring. So if you take the relaxed length minus that, right, then you'd get the distance compressed right there. Okay, so here's your formula for elastic potential energy. Potential energy of the elastic portion is equal to 1/2 kx squared, and that should look very, very familiar, right? That's almost exactly the same formula as kinetic energy, right? 1/2 times the k value times x squared. The k value is defined as the spring constant, right? So it changes depending on what kind of spring you're using. And you know this, like if you take a really small spring like the one that's in a ballpoint pen, you can take that spring and you can stretch it pretty easily. But if you take one of those springs that are like on those trampolines and you just try to do it by hand, those things are really tough. They're very, very strong. Or if you take like the giant steel springs that are doing the suspension in your car, like those are also really hard to move as well. So anyway, so the spring constant is it's a constant that really helps us put a value on how strong the spring is. Okay, and the higher that K value is, the stiffer the spring is. And it's measured in this unit here, newtons per meter. Okay, so remember, energy is in newtons, Newton times meters. The spring constant is in newtons divided by meters, and that's so that the these values cancel when you square the m, and so you still end up with nm, right? Newtons times meters is the same as joules. Okay, the SI units for elastic are just joules, same as potential energy of gravity. Okay. Alright, so here we go. A 2 kilogram mass is attached to a vertical spring, and the spring is stretched 10 centimeters such that the mass is 50 centimeters above the table. Okay, what is the gravitational potential energy associated with the mass relative to the table? So we've got the table, right? And so we've defined this. Well, this is when our potential energy of gravity is equal to 0. So that's our 0 value. And we've got the ceiling up here, and then off the ceiling we've got some mass that's attached to the spring, and the mass is 2.00 kilograms, right? And then it tells us that from here to here is 50.0 centimeters, and then from here to here is 10.0 centimeters. Okay. All right. What is the gravitational potential energy due to the associated with the mass relative to the table? Okay. So potential energy due to gravity is equal to mgh. Okay. The mass is 2 kilograms, so that's easy. All right, 2.00 kilograms. All right, the gravity, well, the gravity is just 9.81 meters per second squared. All right, so on and so forth. And then the height above the table, well, that's in centimeters. The height above the table is 50 centimeters, so we divide this by 100, and so that would be 0.500 meters. Okay, so we'll plug that guy in here, 0.500 meters. Okay, so you could probably do this in your head. 2 times 0.5 is the same thing as 2 divided by 2, which gives you 1. So that means our potential energy due to gravity is just equal to 9.81 joules. All right, so that's the potential energy due to gravity of the mass relative to the table. Okay, what is the spring's elastic potential energy if the spring constant is 400 Newton meters? All right, so this is talking about the same spring, so we know that the potential energy of elastic, I'll just write capital E just because I'm too lazy, is equal to 1/2 K times X squared. All right, and X is that change, so we have 1/2, all right, and it says the K value is 400, all right, and then X squared. Well, the X value, remember we defined the X value as the distance that it's compressed or stretched, okay? So the distance that it's stretched, it says that the spring is stretched 10 centimeters. All right, so our X value has to be 10. But remember that it has to be in meters, so it would be 0.100 meters. And we're going to square that sucker there. Okay, so we plug that in. We say 1/2 times 400, 0.5 times 400 times 0.1 squared, and we get 2. That was easy. But yeah, all right. 2, and then sig figs, this has 1, so we'll say 1 sig fig, so 2 joules. So that's the potential energy of the elastic. Pretty sweet, huh? And that's it. We'll talk about mechanical energy, conservation of energy in the next one. Do the practice problems. Make sure to do those text problems. It'll help you a lot when you're preparing for the checkpoint. Let me know if you have any questions.